Thank you very much for the introduction. And we are Team 8365 Gearmasters, and today we're going to present about wire management and CAD. So just to reiterate, we are a community-based team from New York City. We're the 4 times New York City Inspire Award winner. We're the 2022 World Championship Think Award finalist and Franklin Division quarterfinalist. And we're at Worlds in 2023, we're the Franklin Division Inspire Award second place, as well as winning alliance. And at MTI, we were also the finalist alliance. So why is cable management important? So first of all, it helps you prevent disconnects during matches, which allow you to reach your maximum potential during competition. As well, it is also able to help protect your cables from fast-moving parts within your robot. It also helps give easy access to your robot and have easy maintenance during in between matches. So some cable management solutions we've implemented this season is cable shielding. So this allows us to protect many very important cables, such as data cables. Another thing we've implemented is zip ties, which allow us to help group cables and route them easily. To help prevent disconnects, we use a grounding strap, which is attached to the robot's power source and grounds the robot to its metal frame. As well as we use ferrite chokes to help dampen ESD buildup. So one innovative solution we have come up with to help with cable management is our cable accordion. It's able to keep cables organized by creating a consistent path for cables as well as protecting them. It is also space efficient as it is able to expand and collapse. It is also modular as we're able to change the length by changing how many plates we attach. And it's also able to change the depth to how many cables you want to attach. As the way it is able to move is vertically, it is also great for vertical slides and vertical lifts. So since wiring is often overlooked, we use our design process to plan out our wiring from the very beginning. Hub placement is also critical as it will be one of the most crowded places of your robot. So during our engineering design process, we first start by setting our design goals, then moving on to creating our initial design. And after testing that initial design, we see if we can face any challenges and any lessons learned from those challenges. From there, we're able to create our improvements and then retest those improvements to see if we see any challenges again. Through that cycle, we're finally able to reach our final design. Moving it on to Preston to talk about CAD.
Thanks, Josh. For the computer-aided design portion of our presentation, we will be mainly talking about Fusion 360 with assembling our robot, and later Rick is going to talk a little bit about Blender. So this is our Freight Frenzy robot, and just a overview. This is our rendering on the left, and we mainly split our CAD files or our robot into separate CAD files. So for example, this robot was split into 5 files, which included the drivetrain, the mid chassis, the upper chassis, the intake, and the outtake. After, all of these files are combined into one assembly file. Another functionality of computer-aided design that we love working with is the animation function. And you can access this function through the top left dropdown, where it usually says design, and select animation. From there, you're going to see that it's a storyboard or a storyboard process, which means that you basically select components and move them individually. As you can see on the right, we actually use this for our judging presentation to better illustrate our intaking process. It's just a little more efficient than it would be if you're actually demoing it in person, and you can play around with the perspectives as well. So for this year, we actually focused on moving all of our parts in the actual main file. So we used 3 types of joints in CAD this year, which include the rotational joint, linear joint, and static joint. You can find the rotational joints on each of our intake and outtake arms, linear joints for all of our vertical slides, and static joints for obviously anything that doesn't move. So as you can see on the right again, we're demonstrating our intaking process, and we found this again extremely helpful when trying to demonstrate the processes of our robot. So moving on, before I talk about actually CADing the cable accordion, or what Joshua had shown previously, I want to note that a cable accordion can actually be built without 3D printing anything. So if 3D printing is not accessible, you can always build a cable accordion out of cardboard or styrofoam and tape the joints as you can see here. But as for CADing the cable accordion, you want to first establish some design objectives, which refers to the design process that we use. And some of these design objectives include the cable width, or keeping in mind the cable width and the number of cables you want, as that changes the channel, as you can see on the bottom right, and as well as the height of your lift, which obviously determines how many plates you're going to use. When actually assembling the cable accordion, you want to, or we use tape so that we can easily adjust our path and make it so that we can achieve that consistency that Joshua was talking about earlier. But overall, it's a very simple design and it's very modular and it can fit any team's needs. I'm going to pass it on to Rick to talk about Blender now.
Thank you, Preston. So to begin, I want to talk about why you should use Blender. So first of all, Blender for FTC only skims its applicability. Blender is not used for like one sole purpose. It's used for everything between animations, game designs, simulations, and much more. The second reason is because with CAD experience, which I know a lot of you do have, it's very easy to get into as a lot of controls and shortcuts will feel familiar. And finally, having an appealing robot will make an appealing portfolio, because you can obviously settle for a lower res, somewhat grainy image of your robot, or you can use a Blender render and instead have a nicer robot to sell your team's portfolio. So to get started, I know there's a lot on screen, but please try to follow along. I'm gonna use a laser pointer. I have some highlights. And when we import our CAD file, I recommend using an FBX file because it will break down our robot into its individual components. So each piece will be its own separate piece, rather than using an STL file, for example, which the robot is like one entire chunk by itself. After importing, we go ahead and remove the main cube. And once we zoom in, we will see like a lot of kind of like a spaghetti mess. What you want to do is hide this all, as these are reference points to where each piece is in this 3D plane. So you don't want to delete it. And so you can actually access the pieces inside your robot as we go on to select each individual component. So in this example, I've selected each piece made of PETG, as you can see highlighted and outlined throughout the robot. And what we want to do is use the hotkey Control L to link all these materials, which just basically says, okay, all these materials are going to be made of the same thing, because Blender may actually import some of the stuff wrong, such as this claw piece down on the left, which was imported as a piece of aluminum rather than PETG. And so for this example, the main four values we play with is our color, and then our metallic value, which basically just gives the piece, the component, a shiny metal look. Our specular value, which just shows how light reflects around an object, and our roughness value, which reduces glare and reflection on the objects themselves. Another example I'm going to bring up is plexiglass, or just glass, because we have to change the surface type from principled to glass BSDF. And for glass, I usually lower the saturation of each value because a lighter value makes it easier to see through glass. And having roughness of 0 will actually help you see it through the glass, as there is no reflection and it becomes completely clear. And then here, just a quick note, changing our viewport from solid view to material view. You can actually see how our materials will look like in the final Blender, just in case you want to double check and see how it works. Moving on to our rendering system, there's a lot. I'm going to talk about this background later, but for now, the default rendering engine, when we click on this little TV icon, is going to be Eve. You do not want to use Eve because it just basically gives your robot a solid look, nothing crazy, no variation. So instead, we want to change to cycles, in which it will actually show the glass, show the lighting better. And when you change, looking at like the CPU down here, it's better to use a GPU because it works faster and it will look better in the end. And it can actually save you a couple hours when you actually have to render it. And I'm going to briefly bring up denoise, which is an automatic setting. And I've set a render here, for example, with a time limit of 5 seconds. And without denoise, you will see a lot of grain in the photo, and your robot just will look a lot messier. So instead, turning denoise on, we can see that in the 5-second render, which is fairly fast, a lot of it's cleaned up and our robot looks a lot better. So now going to the background, the little cube you saw earlier, the white cube, we start off by adding mesh plane, which will pop up under our robot in the center here. And when you select the viewpoint up here and zoom in, you can kind of see the plane intersects. And I'm going to bring up grab once, but you use grab a lot, but just obviously, as it sounds like, you grab a piece and move it. And you can combine this with hotkeys X, Y, and Z to lock it to these axes. Or if you use a mouse, which is always recommended for CAD, you can press down onto the cursor button, the scroll wheel button, and it will lock onto those themselves. After adjusting that, we can change our mode after selecting a plane, which is important, to edit mode. And we can choose edge select, which is this faintly blue box in the middle here. And we can select the plane edge and extrude it along the X and Y axes by pressing these hotkeys. And once after some adjustments are made, you can have a plane that looks like this in the background behind your robot. Or you can extrude it along the Z axis instead. And so you can have that little box as you saw earlier. Moving on, we're going to talk about the setup for the scene. So the first thing I'm going to talk about is lights. For your lights, I delete the first light that Blender gives you, and instead I add a light in the middle here because it just pops up right by our robot. And then once you set up that first light, you can Shift-E to duplicate it, copy over the same values, and then grab it to pull it out, readjust it. And actually, moving on to our camera is a little bit different because there's this little hidden arrow button that to pop out here if we actually want to set it up for our render. And by locking it to our 3D cursor and our camera view, we can move our camera easily when we access view camera on the top left of your keyboard with the tilde button. And as we move around as we normally would, our camera will follow us. And this little frame here will show us what we will see in the final render of our robot. And using tilde again, we can exit out from camera view and our camera will be set up there. Finally, lighting. Lighting is probably one of the hardest parts, but simply put, there are two main types of lights, which is having a higher radius and a higher power, or a lower radius and a lower power. And what this basically does is, even though I use the same power, you can see on the left here, there is no shadow cast on an intake, as a wider radius spreads light more evenly. And then for the lower radius, you can see a shadow here as obviously lower radius spreads light less evenly. And overall, using a simple rig of a plane, 2 lights with low radii, we can get a beautiful render of our robot that will spice up our portfolio. Thank you, and let us know if you have any questions.
Don't see any questions in the chat. Anyone have any questions in person? Okay, someone asked, how long does it take to finish a full render of the robot?
So your renders are completely CPU and GPU dependent. I have a CPU and it's fairly, not strong, but fairly decent. So it can take up to like 5 hours. With a GPU, it can only take up to like 1 to 2 hours. And it also depends on how much lighting you put and how much is in the actual scene itself. So it's really dependent on how much there is to calculate there.
Okay, I think there was another question in the chat. How much time do you spend on CADing the robot?
Yeah, sure. I don't think I could put like an exact number of hours on it, but we do run through many prototypes. I know with the drivetrain this year, we especially had many different forms and many different files. And after we were happy with that, we started building on the intake. So it does take a considerable amount of time. But yeah.
No more questions. Okay, well, give it up for Gearmasters. Thank you.
Thank you.
Actually, there was one more question. What CAD learning resource do you recommend?
Oh yeah. So as for like a CAD learning resource, I mean, I specifically didn't use any resource. I kind of just like started playing around with the different functionalities of CAD and just exploring the application. Um I think a lot of it you can also just like watch videos online and stuff like that. But I think it's easy if you can give yourself a kind of like a project and an objective and see what you need to do with that. And kind of build experience from there.
Thank you.